briefly how we can check the proof. So in fact, we use the fact that for any compact subgroup K of our group, the map which sends the space of the representation to its fixed vector by K is a bijection between irreducible smooth representation of G that are ramified with respect to K and the simple modules of this Hecke algebra. And now, because of the previous result, since the Hecke algebra is commutative, then the simple modules have to be one-dimensional, so they are characters. So this is the first example of an ramified representation, provides the first example of representation which are called to be of depth zero. So initially I was given the definition of depth, which was introduced by Moy and Prasad and using the Bruhat-Tits, but then I have realized that I have would take too much time, and so I would just give an example of representation of depth zero, which are the easiest one to be constructed. So when you have a p-adic group in the building, you can take a point in the building and consider a parabolic subgroup that we have seen already before. Can have a nice definition of parabolic subgroup in a more conceptual way, but if you think of GLN, the same way that we can define the Iwahori subgroup as the inverse image by the reduction map from OF to the residue field, the inverse image of a Borel subgroup. Here, instead of taking just a Borel subgroup, you take more generally a parabolic subgroup with coefficient, parabolic subgroup of GLN over FQ, and you consider the inverse image, and you get a subgroup of GLN over OF, and it is an example of parabolic subgroup, and all parabolic subgroups for GLN OF are conjugated in GLN F to such a group. So now when you have a parabolic subgroup, so if you have GLN F, inside G I have maximal compact subgroup, and what I was saying is that we can consider the reduction map, the projection. If you have a matrix with coefficient in OF, you take the similar matrix, but we reduce each coefficient, each matrix entries into element of FQ. And so here I'll take Borel, block triangular matrices, and this is, say, parabolic subgroup. So this group, maybe I will call it G bar, G blackboard, and then if I call this map rho, then I will call G X the inverse image by rho of P. And what is X? X is a vertex in the building of G, which corresponds to my maximal compact subgroup case. So this is a parabolic subgroup. And the nice thing is that now we have an exact sequence Gx. Here I have something that I will call Gx bar, which is a Levy subgroup of my parabolic P, which is given by just the block diagonal matrix here. Yeah. And here is what is called the pro-unipotent radical of Gx. And the depth zero representation are the representation of my group here, G, which admits invariant vector under the action of this group. So in particular, if you consider unamified representations, they have invariant vector by all that groups, or in particular they have depth zero. And also, instead of, you can consider the special case where P is just the Borel subgroup. In that case, Jx is an Iwahori subgroup, and so requiring that the representation as fixed vector by the Iwahori subgroup, it will be same as it would be enough to say that they have Iwahori fixed vector by the pro-unipotent radical. So sorry, if a representation has fixed vector by a parabolic subgroup, and this case is an Iwahori subgroup, then of course they have fixed vector by its pro-unipotent radical, and so they have also depth zero. But in depth zero we have more. Just a comment for this little zero here. Yes, because it's kind of common notation now. For the reason that in general is so we have two notions of parabolic subgroup. There is a generalization, which this one would be the say connected parabolic, and there is a bit more general notion in which the group here is still a reductive group defined over FQ, but not necessarily connected. And in that case, we will use the notation G sub x for this group, and G sub x0 will mean the corresponding group with a connected reductive subgroup. Okay, but I will not enter in this sexuality here. But just to mention that, in fact, to study this kind of representation, it's useful also to understand, to have a good understanding of the representation of finite reductive group, but possibly disconnected ones, which is known. Okay, and the nice result, I mean, the important result is that we have a good description of irreducible depth zero, especially when they are supercuspidal. So yesterday I defined the notion of supercuspidal representation, which does not occur in a proper parabolically induced representation. And so if I can consider a supercuspidal representation, which is irreducible and has depth zero, then they are characterized by this result, which was proved independently by Morris and by Moy and Prasad. So there exists a maximal parabolic subgroup of our group G, and also a representation of the normalizer of a parabolic subgroup, which has the property that its restriction to the pro-unipotent radical is one isotypic. So I take a in this example, I will take a representation here, a cuspidal representation, and maybe I will take here. I will inflate it to a representation of a parabolic subgroup, and then I will extend this representation to the normalizer of a parabolic and induce. And the point is that if I take the disconnected parabolic, then I will get an irreducible representation by induction, and any supercuspidal depth zero can be obtained by this procedure. So here is essentially the example that I was trying to explain on the blackboard. So this is what I just said. You start with the vertex in the Berlin. Consider the normalizer of K0, which in case of GLN, this normalizer is F close time K0, and start with a cuspidal irreducible representation of GLN FQ, which is the reductive quotient of K0, inflate it to K0, and then extend this inflation to F close K0, and then compactly induce, and you get an irreducible representation of GLNF, which is supercuspidal and which has depth zero by construction, and any depth zero representation supercuspidal depth zero representation can be obtained in this manner. And this is the general result, and so it's very useful. So now just one word, a few words. If I take a representation which is not depth zero, so that is a construction which was which started many years ago by the work of Howe and Moy for GLN, and then was extended for all the representation of GLNF by Bushnell and Casco, and later in around 2002 there was a construction by Jacques which extended this construction, this idea using the buildings thanks to a previous work by fundamental work by Moy and Prasad. So they extend this to so Jacques obtained a construction of all the supercuspidal irreducible representation of a group G, which is so it's any group G which has a property that it is quasi-split and it splits over a Temley extension, and with a condition on the residual characteristic, which is that P is large enough. This was proved by Julie Kim, that if P is large enough, then we get all the representation in that case, and more recently, the bound for P was first made explicit and also lower. So now the bound is that P should not divide the order of a Weyl group of G. So these are resolved by Fenton. So now when P does not divide the order of a Weyl group and G is quasi-split and split over Temley ramified extension, we have all the irreducible, all the supercuspidal, and by using the theory of types, we also have all by construction of Kim and Yu. We have also all for any S, we have a type. Not just one actually, but there is also a question of more than one type. But and when P is small, I mean divide the order of a Weyl group. If the group is a classical group, a symplectic group, or special orthogonal group, or unitary group, there is another construction which is really a generalization of a Bushnell-Castle construction when P is odd, which is due to Sean-Stevens, and we also have all the supercuspidal. And the two constructions in the intersection of a definition domain, they coincide. And when P is 2 and the group is classical, we have very few results, but some recent results by Enyart and Hoy, for instance, for some interesting representation. Okay, so I will not interrupt in this because I think it's not directly related to the main subject of the summer school. So I will come back to Hecke algebra. And first, guys, so I will forget the supercuspidal and I will go to more on the other one where we are really Hecke algebra occurring in the picture. And first, I will do the group which I've already seen in Petra talk, Coxeter group. So I will be a bit quick on this. So we have already seen that it's a group which is generated by a set of elements which are of order 2 and which has means the following presentation. So the element, so S square is 1, and if I take two elements which are not equal, which I should have said that S is not equal to S prime, then the order of a product SS prime is a certain integer, it's a certain integer MSS prime. Okay, and this group could be finite or infinite. We are used to call the equality where S squared equal 1 are quadratic relations and the other one are braid relations. And the reason is that in fact any Coxeter group can be constructed as a quotient of a group where you forget this condition, the associated break group. And also these relations are very interesting because you can try to make new relations from that, to kind of quantize them, and is how you will define an Hecke algebra. This will come very soon. So just two examples of Cox-Hecke group, the symmetry group of n element, a set of n elements that we have already seen, and the generalization of it by considering the semi-direct product of Sn by plus of -1 at the power n, or also called the wave product of Sn by the subgroup 1, the group 1 plus of -1. And this one is it's called an hyperoctohedral group. And it's a group, it's called of type Bn and Cn. So for instance, if you take a symplectic group, Sp2n over Fq over F, its Y group as type a type Cn or Bn is the same. And the same for SO2n plus 1. And again, we have already seen the notion of a reduced word. And here I would like to have a name for the number of elements in an expression of an element of W as a minimal product of elements in S. And this number is what is called the length of W, denoted by L of W. So now we can define the Hecke algebra attached to that Cox-Hecke group. So in addition to the group, you will consider a function which attached to each element, to each element of order 2, to each generator S, QS. So I will in general, you could take for QS just a non-zero complex number, but in all the applications that I have in mind, for p-adic group, QS will be a real number, and in fact it will be a power of the residual characteristic, the power of P. And we require the following condition satisfied. So if I take two elements S and S prime which are in the same W conjugacy class, then they are the same Q. So QS is equal to QS prime. And if you fix this, then it's possible to show that there is a unique, and it's not very difficult, but there is a unique algebra structure on the C vector space generated by element TW with W is in W, but with satisfying the following properties. So the T of trivial element is 1. These are what I was quadratic relation if Q is 1, you just recover TS square minus 1. Sorry, TS square is equal minus 1 equals 0, so TS square is equal to 1. So this is a deformation of a quadratic relation in the Ray group, in the Cox-Hecke group. And this is just the bread relation that I had before, but I like to write like this, but it is so if you take the relation before, so SS prime at the power M SS prime is equal to 1, and then you develop this, and the element S and S prime are order 2, so you can pass them on the other side, and you get a relation like this between the S and S prime, and so you take the same relation for the T. And one more relation. Now, if I have the element T sub W, W prime is equal to the product of TW with TW prime, if the length adds. So if the length of W prime is the sum of the length of W with the length of W prime. So this is the Hecke algebra that the kind of Hecke algebra that you will have that will occur study of p-adic groups. I mean, we have kind of generalization of these ones. And you will see that you have two already algebra. Because you can take for W the finite value group, so ng of T mod T, but T is a torus, or you can take a Coxeter group and the affine value group, so infinite Coxeter group, and we will have a different kind of algebra. I mean, similar kind, but another one. So, since we were looking at the building, I would like to give a few words about how we can recover these parameters. So the QS are usually called the parameter of the Hecke algebra. So how we can view them just on the building. So I just briefly recall a few things that we have already seen before in Petra talk. So chamber complex is what I call chamber complex is a simplicial complex X, such that all the simplices are contained in a maximal one, in maximal simplex. And if you take, and we tell the property that if you take a pair of maximal simplices, then you can find a chain of adjacent maximal simplices in X, starting from your X going to Y. And then we have a notion of thickness. So the chamber is called, the chamber complex is said to be thin if each facet of a chamber is a facet of exactly two chambers, and it is called thick. This is something that we have already seen. If each facet of a chamber is the facet of at least three chambers. And as we have, as Petra has explained, an important example of thin chamber complex is given by the Coxeter complex, which is associated to a Coxeter group. And now we will, attached to p-adic group, we'll have thick building, and we can precise a bit more about the thickness. And for this, I'll consider the following objects. So a system of apartment in a chamber complex will be defined to be a set of thin chamber subcomplexes, such that if you take a pair of two simplices, you can find an element A, an apartment. Of course, you know that there is an apartment which contains both of them, and you require that this apartment is in our set, in our system of apartment. And also, if you take two apartment A and A prime in A, they contain a common chamber and a simplex X, which contain a complex chamber and a simplex S. Then the chamber complexes. There is an isomorphism, of chamber complexes from one apartment to the other, which fix point-wise the chamber and also fix the simplex X. Then, when we have this, you can define, also we have already seen that a thick building, which is a thick chamber complex which has a system of apartment. And then we can also show that when you have a thick building, there is a unique maximal apartment. And so we can assume that we can talk about apartment without precising which is the system of apartment that we choose if the building is thick. And also we can attach to the building a Coxeter system. And in that way that we have a property that every apartment of every apartment of X is isomorphic with the complex sigma of Ws, and so this gives us a fundamental chamber, and also we can label the facet of a chamber by element of S. And so, as a consequence, we can label the facet of a chamber of a building. So this Coxeter system is usually called the type of a building. Okay. So now I will take a building X of type WS, and then I will introduce the notion of thickness. I will call thickness of S the set of tuples ds for all the elements of S, where ds minus 1 is the cardinality of a set of chambers which contain the fundamental chambers facet labeled by the element S. And so, if you think what this, the building is thick even and yet this ds is at least 2 for all the S. And the building will be said to be locally finite if the ds are actually finite. Using this notion, these ds are very closely related to the parameter of my Hecke algebra. So, and they are related in the following way. So I fix an Iwahori subgroup of G, and we define the algebra attached to this Iwahori algebra as the convolution algebra consisting of all compactly supported left and right I-invariant functions. So I take functions on G which are compactly supported, and I require that they are invariant, bi-invariant by the Iwahori I. Sorry. And then, so this is the algebra. It's a similar algebra as the one we had before with maximal compact, but with respect to the Iwahori subgroup. And when we have this, I start with a building. I have the ds, which gives a thickness of the building, and then I denote by q sub for each s, each reflection s in capital S. I denote by q sub s the inverse of the ds. And then an important result is that the Iwahori algebra is isomorphic to the algebra of the affine the group of G, and not the affine, but the extended affine. Okay. Assume that they coincide, which is the case in many situations. Then, and the isomorphism from here to here is just to take an element TW and you and it, okay, it is going the other way because TW, because at the beginning I had written my isomorphism in the other direction, and so I take an element here TW and I send it to -1 at the power of the length of W times the square root of QW of the characteristic function of the double coset IWS. So this isomorphism is actually doing it. And this is okay, to explain the notation QW, because I have introduced QS, and for QW, if I take an element W which is reduced, so it is a product, and it should be in W, not necessarily fine. And W is a product of element S1, SR. I take a decomposition of minimal length, and then the QW is just defined to be the product of a QS. So I like this result because this is a Coxeter group, and so it is living in a Coxeter system, and we add a function Q. So we have a Coxeter group, and we impose a certain function Q. But here it's in some sense much better because we have the group G, and thanks to the building, the Q, the function Q is, so of course the group W is given, but also the parameter QS are given by the building. So they are intrinsically attached to the group. Okay, and I especially like it because we will see very soon generalization of this situation, and in this generalization, I do not know if it is possible to make such a nice relation. Okay, so these are a few notation in order to introduce this generalization. which will be called affine Hecke algebra. Essentially, the generalization is easy to, so as before, I have a Borel, and I would like to replace my Borel by a subgroup which is more general, a parabolic subgroup. And here I will replace the Iwahori subgroup by a parabolic subgroup, essentially. And to do that, I need the notion of a root datum, which is would be attached to my p-adic group G. It will be just a quadruple where I have X and Y, two abelian group of finite rank with a perfect pairing between them. And R is a subset of X and R check a subset of Y, both non-zero. A subset of finite set of roots and co-roots, and the bijection with a bijection between the root and co-root, which have a property that alpha check is equal to 2. Okay, and then for each root, I define the corresponding reflection. So it will be my element S. So it's defined like this, and you can check that it's a reflection, but S squared is the identity, and by construction, and I want that it stabilized of the subset R, and exactly the similar condition on the dual side for Y and R check. So it's often useful to have what we call a based root datum, so fixing the basis of the set of root R. And then we can consider the group generated by all the roots, which is the same as just considering the group generated by the S alpha, where alpha are in the basis. And so this group is a finite Lie group. And when I have a finite Lie group, I can make the extended affine Lie group, which is the semi-direct product of this group by X. And so we can describe it as element of a form WTX. So the TX is for the translation attached to X, and the product, multiplication is given as follows. So you multiply the element in the finite Lie group, just direct product, and for the translation, you use the action of a finite Lie group on X1, and you add X2. So if you look at this, it's a description of a semi-direct product. So inside this group, so I call it, it's called an extended affine Lie group, so it should be an extension of something which is called an affine Lie group, and this was the reason for this slide. So the group. This group WX acts on the vector space X tensor R, and so I can consider the hyperplane of the element X in X tensor R, such that the co-root evaluated at X give the value n, where n is the number, an element in Z. So the collection of this hyperplane is stable by the action of the extended Lie group, and so it divides my space X tensor Z into open subset, which are called alcoves. And then I can consider the subgroup WF for affine, which is generated by the reflection around with respect to these hyperplanes, and it is a Coxeter group, and which has nice properties, which is called an affine Lie group, and we can attach to it a certain set of reflection, which is given by the reflection with respect to the walls of a fixed alcove at A0, and then this the this pair W half S half is again a Coxeter system. And when we have this, we can consider the middle product. So the externally defined value WF is actually an extension of the defined value WF by a certain group omega, which is the stabilizer, which is defined to be the stabilizer of the fundamental alcove A0. And we can also describe the length function on the affine group. And if you want to have a length function on WX, you just make extend it by 0 on omega. So omega are the element with length 0. This was an example, but maybe I will skip it because not much time. Because I would like to have time to give the definition of the affine algebra. So I fix the following. I fix an irreducible root datum with finite value group WF. I fix Q, non-zero, positive real number, and I also fix two what I would call weight functions, so two functions from the set of root to C, but I assume that they are invariant by the action of a finite value group WF, which is by definition the value group attached to matrix system, so the value group which is generated by the element by the reflection in R. And I require that if alpha is not cannot be written as the sum of two roots, then these two functions in fact are just equal. So this case is some case which only occurs in the situation of group of type Bn, but we have to consider because it occurs in life. But in much of the case, we just have one weight function lambda. Okay. So this takes care of the weight of these two conditions are for the parameter, and then I need the translation. So the translation I will just write them like this. So we consider the group algebra of X, C of X, now with a standard basis, and I will denote traditionally the standard basis is denoted by theta X, where X is an element in X. And then this is the algebra of my finite value group, which is a Coxeter group that I have defined at the beginning. So Q is fixed. And if you take all of this, you can prove the following. But there is, which is a generalization that we have before in this case, but now I am using it. There is a unique algebra structure on the vector space if I consider the tensor product of Cx and H of WFQ. There is a unique algebra structure which satisfies the following property. First we embed both the group algebra of X and the eco-algebra of WF as sub-algebra of this tensor product. And secondly, when you take for a root, simple root alpha, the root in the which corresponds to the basis of my root system, and an element X in X, there is a precise relation. So you can define the action. So if you want to compute theta times Ts alpha, it is equal to Ts alpha theta S alpha X plus some collected term, and the collected term is this one. So it's Q at the power lambda alpha minus 1 plus theta minus alpha at a certain power, which is lambda alpha plus lambda alpha star alpha mod 2, plus the similar one but with a minus, and then a certain fraction. And the point is that the result is that there is a unique algebra structure satisfying these two properties, and you get an algebra, and this algebra is an associative one. And So this description is usually called the Bernstein presentation of this algebra. And why? Because actually we have another way to construct this algebra. Actually the part which is attached to the not the extended Lie group but to the affine Lie group. So in my first case here, I have taken the extended affine Lie group, but I can also do something for the affine. Okay, sorry. Now I assume that, so I have my parameter QS, and I assume that, this is not well written. So I want to define parameter QS. So I started with my weight function lambda, lambda and lambda star, and for any alpha, I define Q sub S at Q at the power lambda alpha for all the alpha. And if in certain particular situation where we have an alpha star with a lambda star which is not the same as lambda alpha, there is a process to define Q S prime alpha. So this is for completeness, but you can forget of this special, this extra things here. And the important point is that now, at the beginning, it's a bit tricky to explain. Here, this algebra is defined by taking the tensor product of the translation bar and the Hecke algebra of the finite Coxeter group. And on the second page, here I have the Hecke algebra of another Coxeter group, but this one is the affine Lie group, so it's an infinite group. But it's here you also have something infinite because you have finite Lie group, but you consider the tensor with product of the algebra, Hecke algebra of finite Lie group with the translation. So the translation gives you the infinite part. And the important result, so this is due to Bernstein, but actually we can find the proof, written proof is in a paper by Lustig on graded affine Hecke algebras. And there is a unique algebra isomorphism between these two algebras. So here you have just the Hecke algebra of a Coxeter group, and here is something which looks more involved, but actually they are isomorphic. But it is this description, which is called the Bernstein presentation of this algebra, which is really useful for the study of representation of p-adic group, and it's useful because it will relate the situation to the representation of a finite Lie group. And if you think of a finite Lie group, it's the normalizer of if a group is split, it's the normalizer of a torus by a torus, and so it is related to the, say, principal series of a representation. So it's easy to grasp. And this one is more related to compact open subgroup, to the description using the affine theory. So this is a bit vague. So there is a unique algebra isomorphism, which is the identity for the finite part, finite Lie group part, and which has this property. If you take x, which is a scalar positive scalar non-zero non-negative scalar product with alpha check for all the alpha, then you send this parameter to the parameter translation parameter theta x. Okay, and I have 1 minute. So
We started a bit late.
okay, thank you. So what I would like to say is that yesterday we introduced parabolic induction on the level of a p-adic group or finite reductive group, and we can do exactly similar process but now at the level of Hecke algebra. So you just take a base root datum, and then J will be a subset of my set of simple root delta, and then from this I can construct another root datum, but which is attached to J. I'll keep the same parameter function, but I just restrict them to the part of the root attached to j. And then using this, it's possible to define parabolic induction. And here, what's very nice is that parabolic induction is much easier. It's not parabolic induction. It's just induction, usual induction from the representation of h, j to h to h, representation of a, which is really nice because you just take a representation of h, j, and you tensor it over h, j with the algebra h in order to get the representation of h. So it's pretty much simpler. And similar, you have a restriction factor. And then it's also possible to define the notion of temperness for this representation. So temperness is easy. So because you define, so I have a torus, which is the homomorphism from x to c star, can define the weight of my representation are the element. So the weight of pi will be the element t, such that these spaces, the generalized subspace are non-zero. And with this, I have a notion of temperness. My representation will be tempered if all of these are the absolute value of t of x is not greater than 1 for any weight, and x in x plus. Also have a kind of generalization, for a weaker notion of essentially temperness. And then the last result. And we also have a notion of long-loss datum. A long-loss datum is a pair given by a subset of delta and an irreducible, essentially tempered representation delta of my subalgebra hi, which is in positive position. This can be defined, but it's a bit technical. And then the main result is the following. Now I can consider the induce of delta, then this induced representation as an irreducible quotient, and every irreducible representation of big algebra occurs as such a quotient, long-loss quotient. The L is that's an irreducible quotient of my representation. And if I take another one, another j prime delta prime, which have a property that the quotient L are the same, are isomorphic, then j prime is g, and the representation delta and delta prime are equal. So it's a very nice result and very useful because it gives a description of a representation of my algebras. So thank you very much.
Questions?
Maybe I wanted to ask you.
Yes.
If we come back to the beginning of your lectures, where you mentioned that L2 of G mod gamma, your first lecture.
Okay, I do not have
L2
yeah.
G mod gamma is discretely decomposable when gamma is tau compact.
Yes.
Are there some specific cases where you can actually completely describe all the irreducibles involved in the spectral decomposition?
Actually, I don't know. I didn't. I guess so, but I don't know. Marcelo?
Yeah, so your definition of tempered representations for the Hecke algebra that you did now for this Iwahori one. So there is all these translations that take a representation of the Hecke algebra and take Iwahori-spherical of the p-adic group.
Yeah, we could, yes.
And then there will be a subset of the tempered representation as defined in the previous lecture of...
yeah, thank you for your question. Yeah, exactly, yeah. If I take a representation which has Iwahori-fixed vector, as we have seen, it would correspond to an irreducible representation of such an algebra, and the notion of temperness, a tempered representation of a p-adic group, which is Iwahori-spherical, will correspond to a tempered representation of the affine equation. Yeah, thank you. And we also have a notion of this square integrable representation also for the algebra, as they also correspond.
more questions? No, then thank you again, Anne-Marie, for this. Thank you all morning speakers, and now we have a lunch break until 2:30.